Dear ladies and gentlemen, Martin Neff, my name, from ARBURG Plastic Freeforming. I want to welcome you to this presentation about our process, ARBURG Plastic Freeforming, and the possibilities we have with this process. ARBURG Plastic Freeforming, using the potential of the freeformer successfully. We have chosen this topic because we want to show you what possibilities do we have with our additive manufacturing process to produce functional parts and also small serial production batches. As an agenda, we want to following the steps mentioned here. First, the introduction to the freeformer technology. We just want to get everybody to the same level. What does it mean? Freeformer, how is the process of the freeformer? And then we take a step back and we are talking about the theoretical fundamentals. How do we use the droplets and how do we calculate the position of the droplets? How do we use those functions in regards of creating a fully functional part? Then, as a next step, we want to look into the part itself, we want to analyze the part, and we also have some examples where we show the result of that analysis. Process stability and process monitoring is from extreme importance because with that you actually know what do you do, how does the part look like, and therefore it is very important to have a stable process and also have the monitoring to guarantee that. We want to then go a step further into the production of small volume batches. When is it worthwhile to look into freeformer technology as a serial production machine? And last but not least, we want to talk about the individualization of high volume products, what we also show in our efficiency arena. In the leaflets you can see where this cell stands. Last page is a short summary of this agenda or of this presentation. Process principle in detail. Just to get everybody into the same boat, here the process, many of you probably know that already, here the process schematics. We have, similar to our injection molding technology, we have here a 15mm screw available, and with that 15mm screw we are melting standard resin, qualified resin. That melt we keep under pressure, and then we have a kind of needle valve gate system. You see the needle, the yellow part, which opens and closes with a piezo actuator. That opening and closing process release small tiny droplets, and we are talking about a maximum of about 250 droplets per second. And on that release of the droplets, we have a platform, and on that platform we are moving in X and Y direction the part, and that's how we create it, as you can see here in this slide very nicely. What is very important, just as an introduction, very important is that we have with the freeformer an open system available. That means you can adapt your process according to the demands, according to your demands of the materials, according to your demands of the parts, the part geometries. That means you have the possibility of really generating a part fast and optimize that part. We will later see an example of how we did that. And very important, again, using qualified standard resin. So a different variety of materials or high variety of materials is possible and it's available, and that gives us a cost efficiency which is nonetheless not comparable to other systems. Also to this introduction, another slide. In this slide we talk about important parameters for quality and stability. That is what we want to have with all our parts, obviously. We want to have functional parts, and therefore the quality and the stability of a part is very important. What does affect this? This does affect it, or is getting affected by the density of the parts, and that can be achieved with a different position of the droplets, also with different layer thicknesses. As possible layer thickness, we have a minimum right now of 150, actually 140 microns, and 350 microns as maximum. The aim is creating a homogeneous dense layer, as you see in the right-hand corner picture. And for that, we have different nozzle sizes available, so that gives us a broad variety. We are talking in the other slides, which are following now, about the middle-sized nozzle, about the 0.2 millimeter nozzle. Let's get this step back. Step back means we are talking about the theoretical fundamentals. What does that mean? That means basically I want to start with the red hand size picture where you can see this fracture pattern. The upper one, you really see a homogeneous dense part, and this is a picture out of a CT scan. And on the lower side, you see not so dense part. You see voids in between. And of course, if you compare the density of those two, if you would compare the density of those two, the lower one would be considerably less than the upper one. So how do we get to that dense pattern? Well, we have different possibilities, and now we are getting back to the open system. We have the possibility of adjusting different layer thicknesses, and therefore we have different density, or we can achieve different density levels. That has obviously an effect onto the build time and also onto the accuracy, which you see in these black colored sketches. If you go to a finer layer thickness, you don't get those larger steps between the layers. And that has a direct influence also on the mechanism, stability, and quality of the part. Let's go a step further into these theoretical fundamentals. The key droplet parameters are shown in this slide. Well, a droplet is actually not a nice spherical volume. It is basically a more longitudinal size-shaped drop, and for that we have some factors in our calculations behind, which you can see here on this slide. Don't get into the formulas too deeply, but what we want to say is basically that the volume of each droplet corresponds with the layer thickness by cubed, and also with the ratio of this shape factor squared. That means if I change the layer thickness, if I double the layer thickness, I give the droplet 8 times more space. In other words, I really need to know what I exactly do when I do some changes in the layer thickness. The same when I change the shape factor. If I double the shape factor, I get 4 times more space for the droplet. These are some theoretical calculations behind, but let us have a deeper look into the practical application, and this is what we want to show in this slide. So if I have a different layer thickness, I can adjust a different shape factor, and that results in different part densities. As you can see here, just some examples in this table. For example, 150 microns layer thickness gives me, and a shape factor of 1.42 gives me a part density of 95%. That correlates directly with the CT scans you see below in the screen colored. We want to go into the direction of the right-hand CT scale scan, where we really see a very homogeneous dense layer. How does it affect when we look at part density and strength. That is what we want to show in the next slides. Let's say we look at a standard part. This is a standard tensile bar. I have here such a tensile bar. And when we say injection molding, the tensile bar of injection molding has 100%. We can see in the green bar that this is the result, what we get with an optimized discharge. Basically, that green bar results into the left-right corner picture where we see a homogeneous layer, and that results directly in a density of 96, 97, 98%. Also shown in this slide, our conventional discharge. What does it mean, conventional discharge? Conventional discharge is a discharge which we use as template and which we give as machine supplier, give with the machine out, which is not optimized to certain specific materials or specific part geometries. So with that, we are in a range of 92%. If we look to the mechanical stress tests, the yield stress and the fracture elongation, you can find the following results. That we are, with the injection molded part, we are in a range of 65 megapascal. And with the optimized discharge, we are in the range of over 61 something megapascal. If we go to the elongation, it was a very surprising result for us that we, even with the optimized discharge, reached an elongation level which was well above 100%. I will go into that a little bit later in the next slides. What does it mean? That means, and you see that in those pictures, the upper picture shows that you can see on the borderline those droplets. And those droplets on the borderline do directly affect the elongation. Respectively, the part breaks earlier. If we look at the optimized discharge on the lower picture, we see that the borderline is really melted also nicely together. You don't see any droplets, and you see a really nice breaking of that tensile bar. How does it look like? It looks like this, and I have this longer tensile bar with me. This is the tensile bar which had that longer elongation over 100%, and with a conventional, we are looking at just this elongation before it breaks, and you can really see in the breaking picture of the surface what was the reason for that. The reason was that the droplets are still visible and you didn't have that dense packing. So another quality effect which we usually see with injection molded parts is how does the surface finish look like? How smooth or rough is the layer? And you see here some values, and compared to injection molding, we are actually we achieve here a very smooth layer. Of course, it's hard to see it now via this video, but please go ahead. We are producing this part in our lab during the tech days. Go ahead and have a look there and grab one of those parts and see by feeling it how smooth the actual surface finish really is. Then let's go to a real application, a real example. As real example, we have selected this functional part. This is a pulley with different functions integrated. So this inner wheel can spin, also this one can spin. We used as material, we used a polyamide, a bio-polyamide from EMS acrylamide. Part weight, we are talking about 61.5 grams. The load bearing capacity was about 100 kg. we want to have obviously a high level of reproducibility, and well, for us important was, or for the designer important was, hey, what do I need to do to improve the part in regards of stability, and how can I get to a more stable part? What they did as a first step is to produce that part, and they put it into a machine where it gets pulled out, pulled apart. And you can see that in this lower section here, it's also shown in the slide, it broke. Where you see this vertical step, it actually broke, and then we could pull it even further until it really dropped through. So the designer knew, aha, I have a weak spot there, so I need to basically improve that area, especially that area, that lower area, I need to improve. And with that improvement, we come very easily and very quickly to a 10% increase of the stability of the prototype. This should just show how quick it is to improve your part. You immediately have the prototype available for internal testing, and therefore your actual development time is much shortened up or shortened down. Systematic data acquisition is a key, very important. What we know from other processes like injection molding, also here in the additive world, it is very important to get the real data of your process, the real material pressure, temperatures, the real discharge, the real torque, the real force, and with that we can correlate to the part stability and to the part density. And it is very important to be able to extract those data from the machine. We do that via OPC UA, server client based, and that gives us then, as I said, more data in regards of looking at the part, how stable is the part, where might be the weak spots of the part. And what you see in this slide, for instance, is an application or is an example of the material pressure in bar compared to the discharge. So we see exactly, is that in a range where we want to have it, or do we have here some features which are kind of out of tolerance. To go a little bit further and show how important it is to have the reproducibility, and actually not how important it is, and more into that direction, how important or what we have already achieved. I want to show you this part. This is a model of our largest machine clamping unit. You can actually, by rotating here, there is a spindle inside, you can actually move those toggle joints. We are talking about over 20 individual parts which were built in one print job. And for that print job, we have 10 high 8 droplets. That means over 100 million droplets. And therefore you can see, you can imagine how important it is to have a process stability and to have process consistency that starts already with the material preparation, how the material gets melted, how homogeneous you get the melt, and goes further until to the movement of the axis. Of course, also discharge of material and so on plays an important role into that. But just to show how stable the process is, we wanted to put this slide in. Let's go a little bit further and into another example. We always say small volume batches. We use the freeformer technology also for internal part production. We have here an application which we use internally, and what we needed here is in this connector, we need a small piece of distance holder. It's called spacer actually. And the question was, or the task was, that we need about 1,200 spacers units a year. And the thinking process internally was, hey, should we use a machine, an injection molding machine, to produce those 1,200, or can we do those on the freeformer? Injection molding machine means our smallest machine, 170S, tie bar distance of 170 millimeters. So we are talking about a smaller mold like that size. Let's look at some manufacturing conditions. We said the all-rounder, when we do it in injection molding, we are talking about 8-second cycle time for about 4 pieces. With the freeformer, we talk about 3 minutes, slightly under 3 minutes per unit. And for us, it was important to see where do we have a break even. We went into this calculation, and we assumed that we have to build a mold here, and that building that mold for a 4-cavity tool costs us around 8,000 euros, roughly. We did then the machine calculation, used all the energy costs, used all the invest costs, and so on, and we came up with the following graph, which was very important, which was very interesting. So you see that we have a break even here at 5,540 pieces. Above 5,540, injection molding would be more economical. Below, the freeformer is more economical. So therefore, obviously, we needed to have 1,200 pieces. We decided to produce those parts via the freeformer. Last but not least, another example. This example is a kind of very interesting example because you can see it actually live in demo running in our efficiency arena. What do we want to show there is basically we want to show the individualization of a mass-produced part. So a part which was produced in a high volume on our injection molding machines. We have just taken here this luggage tag, and this high volume part should get also individually further improved, and we could select, or a customer can select here different symbols according to his wishes. It can be also some other symbols. We just have chosen those. And as I said, an injection molded part get in that way individualized, and we are even talking about and going back down to piece production number 1. Here in that part, in that luggage tag, we have an NFC chip where we have several different data, also the whole production data on that chip. Internally there is the chip. We do here from the freeformer side inline slicing of the individual geometry. We also need to adjust the height automatically because we have here tolerances which we need to compensate, and all these production steps are interlinked, and we can see all the production data of each step in our cloud system. Via Handy you can even get the production data out, or via NFC reader you get the production data out. So a classical Industry 4.0 application. Please have a look into our efficiency arena to look at this part. As a summary, just last but not least, but we want to focus on this again. Open system. Open system is important to have the possibility to adjust the process parameters to your specific parts, or adjust the process parameters to your specific material. That is very key. Also very key, another point is that you have freedom in selecting the right material. That gives you a larger flexibility and is also more cost efficient. Of course, it is a new process, and therefore technology experience, application experience is needed, but that can be learned, and our team is helping you in that regards. If there are not any further questions, I want to thank you for your attention and wish you a nice day here in Losburg at our Technologie Days. Thank you very much.